Okay, good evening. Week 5, Thursday. I'm hoping that tomorrow evening, the results for term test 1 will be out, and I'm hoping to announce who has to do correction also tomorrow. Okay, but for today, I'm going to lecture the shearing stress using thin wall analysis. Okay, and we started thin wall last week on Tuesday. So let me quickly recap about thin wall analysis. Okay, very quickly. So thin wall analysis is basically what the difference is you have to consider the split of the shear flow. Okay, like when it's box beam, one of the Q goes flow to one side, the other of the Q will flow the other side. Okay, so this is where when we do analysis later on, you'll see me use 2Q. Okay, so the difference between thin wall and non-thin wall is for thin wall analysis, the thickness is usually perpendicular to the shear flow direction, right? This is the thickness. Whereas for non-thin wall, right, the thickness at the flange is taken as the thickness that you see over here. Okay. Then we know in thin wall analysis there is either going to be box beam or wide flange. Okay. So the difference is the number of terminals. For box beam, you have one terminal above the centroid and one terminal below. In a wide flange, right, you can have two or sometimes three terminals. Okay, so that is a distinct difference between wide flange and box beam. And if we want to just find the stress at point alpha, for wide flange, you just need to consider this area. Why? Because the terminal on the left hand side and the terminal on the right hand side are independent. Okay. A rule that we state in terms of designing the shear flow is the Q. The shear flow is controlled by the web. Okay, so the web controls the shear flow. Okay, so I'm going to design. Okay, I did this already. I'm going to quickly recap. So we're going to look at this structure over here. Okay, I'm going to do the shear flow design again. Okay, I'm going to do both, and then I'm also going to take. By the way, this is one of the most abstract topic in structure analysis. Okay, but it's not difficult. You just need to remember some rules. So I want to highlight the fact that the main web. Okay, I'd like to show that the main web or the continuous web controls the direction of shear flow. For this case, it's our Q. Okay. So I want you to have a look. What do I mean by that? Okay. So now let's say our our V is coming from the top. Okay. So this is our V1. Our destinate our transformation, which is this is our Y and this is our Z. Okay. So the continuous web. Okay. So this is what we call our continuous web. Why continuous? It from the top, okay, if we call this to the top and we call this the bottom, it's continuous. There's no broken. Okay, it's not discontinuous. Over here is also our web, but it's discontinuous. Right? It's not continuous from top to the bottom. So the continuous web controls the direction of shear flow. So I'm going to design our Q now. So this is how our Q, and this is how our Q is moving now, or the design of our Q. Okay. So this is how we start the design. Okay. So that is how Q is going to flow. Okay. This is what is controlling the flow. It will start from top to bottom because Vy is flowing downwards. Okay. So now we have to complete the rest of the shear flow. Now you have to remember it's called a shear flow. The idea is also similar, similar to fluid flow. Okay, how a fluid is flowing. So now if we want the fluid to flow from the top to bottom, we know that the direction of the flow has to be coming in this way. Okay. So where it started, okay, this is known as our terminal. Over here, this is also known as our terminal. So at the terminal, the first moment of area is equal to 0. Okay. When first moment of area is equal to 0, the shear stress is equal to 0 also. Okay. And then if we look at the bottom of the structure below the centroid, right, we know the flow will go this way. So this is again another of our terminal. And then where it ends, this is again our terminal. So this is how you design your shear flow. Again, at the terminal, Q is equal to 0. The shear stress is equal to what? 0. Okay. Now, let's look at the next structure over here. Now I'm going to flip my V. Okay, I'm going to flip my Vy. Right? I'm going to flip my Vy down here. Now, this is our Vy. Right? So now the Q, again, is controlled by the continuous web. Now the continuous web is not at the center anymore. Now the continuous web is the left and the right. So over here, this is the continuous web. This is also the continuous web. So the shear flow now will go this way. Right? Then it will come over here. Right? Wrong. And then it will go from here. So over here, this is our terminal. Okay? And then over here, this is also our data terminal. Okay. So at the terminal, again, the shear stress is equal to 0. Okay. So I hope you understand what do we mean by the continuous web controls the shear flow. This is important. Okay. Right. Anyone, any questions? Is this clear? Okay. I don't hear anything. Okay. So we are going to go into example number 1. Okay. Example number 1. And the example is available on Avenue to Learn. I hope Okay, so you can get into Avenue to download this example. So knowing that a given vertical shear cause a maximum shearing strength of 10 kilopascal in a head-shaped extrusion, determine the stresses at point A and at point B, right? So what is given in this example is we know that tau max is equal to 10 times 10 to the power 3 psi. Okay, so that is what has been given. So now the thing to consider is we are going to apply thin wall analysis. Okay, we're going to apply thin wall analysis for this case. But before we while applying thin wall analysis, we need to determine the location of tau max. Okay, so this is pretty tricky. Okay, and I will explain to you why this is a pretty confusing problem. Okay, so if we were to load up this structure, okay, we are going to design the shear flow first. We're going to design the shear flow. Okay, Q. So over here we're going to sketch our shear flow, but I'm going to sketch also the location of the centroid. Okay, so this is just a sketch. Okay, so this is the location of the centroid. All right, so we know that Vy is coming from the top. Right, this is your Vy. So we're going to design the Q, right? So the Q will go will go left and right. And then will flow downwards. And then over here. So what we realize in this problem, this is a very interesting and confusing problem also. We know that this is our terminal, right? And we know this is also our terminal. So this one is weird in a sense that at the top, only above the centroid has one terminal. Below the centroid, we have two terminals. So how will this affect our analysis? Okay, how will this affect our analysis? So pardon me, I have to use another software to create a box that I could move around. I'm just creating a box, okay? So you guys don't do this, okay? I'm just creating a box, and I'd like to fill it. I'm feeling a bit orange today. Okay, and I'm going to paste on the next I'm going to take this whole thing across.